Hello everyone and welcome to the 7th lecture of the Operations Management course. Today we will talk about some extensions to the economic order quantity model. We will start by reviewing the main elements of the EOQ model. Then we will give a hint on the sensitivity of the EOQ formula. Then we will talk about some extensions that include considering safety stock, extending the economic order quantity model in the case of finite production rate, which is known as the economic production quantity model. Then the quantity discount models, how quantity discounts can affect our calculations. Then we will talk about resource constraint multiple EOQ systems, which considers situations in which we talk about several stock keeping units and we have some constraints related on the storage size in our warehouse. And then we will talk about a policy called power of two policy, which is helpful when we talk about multiple items that are being considered simultaneously via using the EOQ model. Let us review quickly the elements of the economic order quantity model, which was presented in the previous lecture. The EOQ model is based on mainly 7 assumptions that simplify the transactions related with withdrawing inventory and replenishing inventory. These assumptions include the demand rate is constant and deterministic. The order quantity need not to be an integral number of units. The cost factors do not change with time. No shortages are allowed. The entire order quantity is delivered at the same time. The lead time is deterministic. And finally, the item is treated entirely independent of the other items. So these are the main assumptions of the EOQ model. Based on these assumptions, the relationships that describe how the inventory level changes over time with the variables and the parameters of the problem are highly simplified, which enables us to solve the problem very easily. So when we put these assumptions together, you will see that the inventory level diagram becomes very simple as represented in this slide. Here, the inventory level diagram, as you can see, is simply straight lines, okay, that represent the withdrawal of items from inventory, the inclined lines, and we have upward lines that represent the replenishment of the ordered quantity, and this continues forever. Now, when you look at this graph, you will see that the slope of the inclined line is always negative D, where D is the demand rate, which is assumed to be fixed. Also, when we decide on the order quantity Q, the value of Q is going to be the maximum inventory level that can be reached for that item. And when we have a fixed lead time of certain value, the reorder point can be determined easily, as you can see here, by looking at the relationship of the inclined line and calculating the reorder point or the inventory level at which the order should be placed. Now, this is the very simplified inventory level diagram taking into consideration the previously mentioned assumptions of the EOQ model. Now, based on these assumptions, the analysis becomes very easy and straightforward. As you can see here, usually the given parameters include the ordering cost, which is a fixed cost that does not change with the ordered quantity, the demand rate, which is assumed to be fixed. H is the inventory holding cost per unit per year. And please be careful about the units that we are using in our calculations. Now, as mentioned in the previous lecture, H can be calculated as the multiplication of the purchase price of the stock keeping unit times the cost of capital, which can be the minimum attractive rate of return of a company. Now, based on the previous assumptions and the given parameters, the only decision variable that we are looking for its value is the value of Q, which is the order quantity and at the same time the maximum inventory level. So in order to determine the value of Q, our objective here is to minimize the total cost, and the main elements of the total cost include the ordering cost per year, the inventory holding cost per year, and the annual purchase price of the item. Now, as you can see here, in this function, we have actually two terms that depend on the value of Q, which is our decision variable, and the third term is fixed because it's simply the multiplication of the price per unit times the demand rate, which is also fixed. So in this case, the part that includes the decision variable Q of the total cost function is referred to as the total relevant cost, okay, as shown here. Now, based on simple calculus, if you want to find the minimum value for the total cost, all what you do is to differentiate the total cost function with respect to the value of Q, which is the decision variable in our case, and then equate that to 0. This will give you a very simple formula that gives the optimum order quantity, which is denoted as here as Q star. It's a very simple formula. It's the square root of 2AD over H. And as a graphical representation of these relationships, as you can see here, we have two terms for the total relevant cost. The first one is the inventory carrying cost, which is a linear function. Another term, which is the ordering cost, which is a nonlinear term. Okay, and when actually these two terms are equal, okay, you will get the value of Q star. Okay. And that's, of course, as you can see here, it appears simply on the total cost curve, which this is how it looks. And of course, this is the optimal point that we are looking for, the minimum total relevant cost value. So this is how simply we do the calculations of the EQ formula. Now, a very important characteristic of the EOQ model is that actually the total cost function is not that sensitive to the value of Q. What do we mean by that? Actually, if you calculate the value of Q star, okay, and substitute in the total cost function or the total relevant cost function, you will get, of course, the minimum total cost value. But then if you decide to have a value that's, let's say, for instance, 20% larger than Q star or even 10% lower than Q star, what you will get is actually you will get very minor difference in the value of the total relevant cost or the total cost value. This means what? This means actually the model itself is not that sensitive to changes to the values of Q star that you might wish to consider as a solution to your problem. So this is a very important characteristic that we will benefit from it actually later in this lecture. Now let us have a look at some extensions to the basic EOQ model. The first extension is related to the consideration of something called safety stock. Safety stock is an amount of the stock keeping unit that is kept in inventory all the time. This amount can affect the shape of the inventory level diagram as shown here. What happens is it's like you have raised the level of the inventory level diagram by an amount that is actually the safety stock. Safety stocks are very important for companies that might wish to cope with changes in their inventory management parameters. And here we are talking about sudden unexpected changes. For instance, if a company might face irregular demand at a certain period of time in which the demand rises above the regular average level, And in this situation, the company might face a stock out of the stock keeping unit, and the company does not wish to have this situation. In this case, they will keep a certain amount of inventory all the time, which is basically the safety stock. Now, when we take the safety stock in our consideration, actually it does not change the calculations related to the determination of Q star value. All what happens here is you have a fixed value for the safety stock, and that safety stock will be added to the value of Q to give you the maximum inventory level that will be reached in this situation. Other parameters will remain the same. Nothing will be changed. The second extension that we will talk about here is the extension of the EOQ model with considering the case of finite production rate. If you recall, the one of the main assumptions of the EOQ model is that when the ordered quantity arrives to the warehouse, it's assumed that this quantity will replenish the inventory instantaneously, which means you have always a straight line that goes up, okay, from 0 to the maximum inventory level, which is the value of Q which you have ordered. Now, in the case of finite production rate, we have a situation in which this replenishment is not done instantaneously. Instead, you have something called the production rate, denoted as P capital, as you can see here. Now, this is the replenishment rate. This means what? This means you replenish the inventory with the value of P, which is given as the number of units per unit time. Now, if you have a value of P, this okay, at the same time when you replenish the inventory, okay, you also withdraw some quantities from inventory with the demand rate D capital. So it's like you have a double effect here. During the period, which is denoted as T1, here you have double effect. You have a straight line that represents the situation in which you add to the inventory with the rate P and subtract from the inventory with the rate D. That's why we have this inclined straight line will have a slope that's equal to the difference between P and D. Now, of course, the maximum inventory level in this situation, which is denoted as H, is not going to be the value of Q or the ordered quantity, because the difference between, of course, the replenishment rate and the withdrawal rate. Now, after reaching the maximum inventory level, you start withdrawing again from the inventory with the given rate D until reaching the zero inventory level, and then you continue the process again, and the cycle is repeated. Okay. Now, the period of time during which you only withdraw from inventory is denoted as T2. So in this case, of course, you have the cycle time. In this case is going to be the summation of T1 and T2. Now, this model is referred to as the economic production model, short for which is shortened as EPQ. Now, when you look at the calculations and the analysis of this model, you will see that the total relevant cost can be expressed again as a function of Q, and Q, remember, is the ordered quantity. Similar to the EOQ model, we multiply A, which is the ordering cost per order, times the number of orders per year, which is simply D over Q. So it's the same ordering cost per year as in the EOQ model. Okay, but the other term, which represents the inventory holding cost or carrying cost, will be different. Why? Because as a matter of fact, when you calculate the average inventory level, it will be affected here by the production rate. Here, this term, this part of our calculation represents what represents the average inventory level. And of course, the average inventory level is calculated as H, the maximum inventory level, divided by 2, just like what we did for the EEQ model. Okay, and remember, the only difference is H is not the same as Q in our case. So the value of H is simply Q times 1 minus G over P. This will give you the value of H. When you divide this value by 2, it will give you the average inventory level for the EPQ model. You multiply that by H, and this will give you the inventory carrying cost. Now, as you can see, the model has the same structure as the EOQ model, except for this parameter, which is this factor, which is 1 minus G over P. Therefore, the calculations will be the same almost, okay, except that the value of Q star now is going to be square root 2AG over H, but H is multiplied by 1 minus G over P. And that's basically how the value of Q star is calculated using the EPQ model. Now, let us demonstrate how to use the EPQ model through a simple example. In this example, we have a bakery which supplies a large number of retail outlets. Our application here is related to how the bakery is going to manage its production. The bakery uses bulk flour at a rate of 2,000 pounds per working day, and pounds here is the weight unit that we are using in this example. Now, this means what this means. Daily, this bakery consumes 2,000 pounds of flour. When the bakery places an order for bulk flour, it's delivered at a rate of 8,000 pounds per working day after a lead time of 5 working days. So now this means what this means. The supply of the flour is done with a rate that's 8,000 pounds per working day. After a lead time of 5 working days, this means when we place an order, okay, it takes 5 working days until the required quantity can arrive. All right. So the cost of placing, receiving, and handling an order for bulk flour is $48, and that's the ordering cost that we are going to have in our model, which is A capital. The holding cost is estimated to be $0.3 per pound per year. Okay, so this will give us the value of H. But here the H is calculated for what? Per pound per year. Okay, all right. Now, we have some requirements in this problem. We will see how to solve each one of them separately. The first requirement says, convert the holding cost to a cost per pound per working day, assuming there are 300 working days a year, of course. Now, why do we need to do that? Because actually we need to unify the units that we are going to use in our calculations. And remember here, the value of the value of D is given, which is the demand rate, is given per working day. The value of P, which is the supply rate, is given per working day. So everything is calculated based on a working day, except for the inventory holding cost, which is given per pound per year. So we would like to convert that. Instead of per pound per year, we would like to have it per pound per working day to unify the units that we are using for the time in our calculations. So this is done very easily here. H is given as $0.3 per pound per year, just divided by the number of working days a year, and this will give you the value of the inventory carrying cost per pound per working day. Now, this value can be used directly in our model without worrying about the units that we are going to have for, of course, the value of Q star or any other calculations. The second requirement says determine the optimal lot size. So this is direct application of the EPQ model. The optimal value of Q in this case is square root 2AD over H times 1 minus D over P. You just substitute the values that we have, and remember, of course, the value of H is the one that we have just calculated per working day, and this will give us 16,000 pounds per order. So every time this bakery places an order, it should order this amount. Now, the last requirement asks for several values. First, determine the resultant maximum inventory level. Maximum inventory level is H, okay, which is simply Q star in our case, times 1 minus D over P, which in this case will be 12,000 pounds. The average inventory level in this case is simply H divided by 2. Now remember, this term is what we are use in calculating the inventory carrying cost. The average annual holding cost is then the multiplication of H times the average inventory value, okay, which is going to be, in this case, $1,800 per year. Remember here, when we calculated the value of the average annual holding cost, we used the value of H, okay, as 0.3 because the units here is per year. Next, the interval between orders. The interval between orders is simply the ratio between the maximum, the ordered quantity and the demand rate, okay, which is basically the length of the cycle itself. So the length of the cycle here is 8 working days per order, okay. Finally, the reorder point. Reorder point is determined by multiplying the demand rate and the lead time. It's 10,000 pounds. So this means what? This means, well, when your inventory level reaches 10,000 pounds, you should place an order. Okay, but the maximum inventory level here is 12,000 pounds. Well, that's fine. Well, this means what? Actually, you will notice here that you have a lead time of 5 working days, right? While the cycle time is actually 8 working days per order, okay? So yeah, I mean, the difference here is not that big. So it's like, yes, the maximum inventory level is 12,000, and when you consume only 2,000 pounds, you should place an order, okay, for the Q star quantity that we have calculated. So this is how we use the EPQ model to treat this problem. The third extension that we are going to look at now is the quantity discount models. What happens in quantity discounts is that the supplier sometimes might wish to promote the sales of its products. And in this case, the suppliers might benefit from reducing their selling price per unit if a customer wishes to increase its ordered quantity. So this means, for instance, if, for instance, I decided that my optimum EOQ value is 375, okay? So the supplier can give me an offer. If I purchase 400 units, this will allow me to have a lower purchase price per unit, and therefore, of course, this will reduce my cost, my total cost. So this is the situation of quantity discounts. Now we would like to take into consideration the effect of quantity discounts on the calculations that we make on the traditional economic order quantity model. Here, when you think about it, you will see that the value of C, which is assumed to be fixed in the original EOQ model, is not now fixed. Why? Because it's now a function of the amount or the quantity that I'm going to order. So this means what? This means the total cost function is going to have three terms that actually are functions of Q. The first term is the ordering cost. The second term is the inventory carrying cost. These two terms are the usual terms that we find in the EOQ model, except of course actually if the value of the purchase price per unit is a function of Q, then the value of H that we should substitute here is going to be another function of Q, if of course we calculate H as the multiplication of C times I. And of course, the third term that we have here is actually C as a function of Q times D, which is the purchase cost per year. And as you can see, of course, now C is a function of Q. Quantity discounts are very common in different businesses, and they are related to something called the economies of scale. That's if the supplier can increase or would like to increase the production amount, the supplier might go for a more automated manufacturing process. And when you have higher level of automation, usually the production cost per unit will go down. So it's like if you purchase more quantities, this will encourage the supplier to produce more quantities, and the supplier in this case will go for a more cheaper way of producing the products, and therefore the cost per unit is going to be down. Sometimes there are situations in which you might have multiple quantity discounts. That's the supplier will give you a certain value. If you purchase more than 400 units, then I will give you 10% discount. If you purchase more than 1,000 units, I will give you 20% discount, and so on. All right, so in this case, we would like to see how to treat this problem, how to find the optimal order quantity Q, okay, given that situation. Now, in order to see how to determine the optimum order quantity, we have first to look at how the value of the unit cost or the price of a unit can change with respect to the value of Q. As we mentioned earlier, in the usual EOQ model, the basic EOQ model, the value of C is constant, fixed. So it's like you have a situation here. If you draw the value of C as a function of Q, it's going to be a horizontal line. But when you have quantity discounts, then you will have some points at which the value of C will go down. Now, how does that affect the total cost function? Well, as you can see here in the figure blue, you have actually for each value, if you draw for each value of C of Q, if you draw the total cost function as usual as we had done in the basic EOQ model, you will see that you have three curves. Like this is the first curve for the first value of C. This is the second curve for the second value of C. This is the third curve for the third value of C. But then, of course, each curve of these three will be applicable only within certain range of the values of Q. So it's like the first curve will be applicable only until we reach this value of Q. The second curve will be applicable only until we reach this value of Q. And the third curve will be applicable only for values of Q that's greater than the last value. So this is how the total cost function will be affected by the changes in the unit cost or unit purchase price, when it becomes, of course, a function of the ordered quantity. Now the question is, how would you treat the usual EOQ model in order to take into consideration the quantity discounts and decide on your optimum ordering quantity? Well, basically, this is the issue of looking at the curve represented by the solid lines here, okay, these solid lines. Okay, if you look at this solid line and the second solid line, okay, and the third solid line, then if you can draw them, of course, then you can easily find the value at which you will get the minimum total cost. In this example here, this is actually the minimum total cost that you can get, and therefore the optimum order quantity is going to be the value here. So this is how it's done. Okay, now let us see how this will be done through an example. So in our example here, we have the value of D is 40 per week, 40 of course units per week. Of course, we assume that we have 52 weeks a year, so we convert this number into the demand in terms of units per year. We have an ordering cost of $25. We have an cost of capital that equals $0.26 per dollar per year. And then we have here the value of C is given as a step function here. The value of C equals 10 when the ordered quantity is less than 300 units. And then you will get a 3% discount on the price per unit when you order more than 300 units. Okay, so this is how the cost function is defined. So in this example, what we are going to do is we are going to calculate the economic order quantity model when we take into consideration the discount. So if I'm going to use the discount, this means the value of C is going to be 10 times 1 minus 0.03. That's getting 3% discount. So in this case, when you apply the EOQ formula, you will see that the value that gives us the optimum order quantity is what is 203, which is less than 300. So this means what? This means you are in a situation in which if you are going to use the curve that represents the total cost function for the quantity discount. Now let me illustrate that for you here. If you draw this total cost function, okay, you will see that this is, let's say, this is how it will look like, for instance. Now here we are using what? We are using the value of C that equals the quantity, the discounted value, of course. The value here is found to be 203, which is less than the value of the quantity discount defined by the supplier. Okay, this means what? Actually, this part of the total cost curve cannot be used, okay, since it's only valid when the order quantity is greater than 300. So this means what? This means this point is not achievable as a matter of fact, and its corresponding total cost is not achievable. All right. So in this case, what we are going to do is we are going to calculate the total relevant cost when we order, okay, the optimum order quantity using, of course, the value of C of 10 units only, which is the regular ordered quantity when, of course, the order quantity is less than 300. Okay, so here the calculations that we have in this line is actually the total relevant cost if you decide to order the EOQ value when your order is going to be less than 300 units. Okay, here I'm not calculating, of course, the value of the EOQ first and then substituting in the total relevant cost function. I'm just doing it directly using this direct formula because after all I'm interested to see the total cost value, not actually the EOQ value for now. Well, C, as you can see here, we substitute the value of C naught, which is 10 in this case, okay, in our formula, and this will give us $21,320. Now, the other option is to order the 300. And why is it 300? Because actually, if you look at the curve that we have just drawn here, okay, the minimum value of the total relevant cost that you can get is at an order quantity of 300. If you order more than 300, in this case, the total relevant cost is going to be higher. That's why we do our calculation only for the value of 300. Now let us have a look at the formula. It's AD over Q, where Q of course is 300 in this case, plus Q times C naught 1 minus D, which is I'm getting benefit from the discount that we can have, plus of course the purchase cost for the order for the, of course, overall demand in the year. Now this will give us a total cost value, okay, that's as a matter of fact less than the previously calculated one. Now this means what? Our interpretation of this result is, well, yeah, you order actually 300 units because this will give us a total cost that's less than the total cost if you order the optimum EOQ value, of course, when you actually order a quantity that is less than 300. So this is how we treat this kind of problems. So far, we have seen the economic order quantity model and 3 different extensions. And in all these models that we have seen so far, we use the economic order quantity model to come up with the optimum order quantity value for each stock keeping unit independently from the other units in the company. Well, in real life situations, of course, this does not happen. There should be some coordination, some limitations that somehow affect when orders are placed and what are the ordered quantities for the different products that usually are somewhat restricted to some practical limitations. Here, in this slide, we talk about a resource-constrained multiple EEQ system. And in that system, we are talking about more than one stock-keeping unit. And of course, for each stock-keeping unit, you have the economic order quantity calculated separately. But there is something in common between these stock-keeping units, which is actually you have some limitations on the maximum inventory level that you can keep at any time. That's why we call it resource constrained multiple EOQ system. So in situations in which you have some limitation on the maximum inventory level, which is naturally the case in most warehouses, a warehouse can have certain limit on the number of units stored, or sometimes you have some financial restrictions. For instance, for as we talked before, actually any item kept in inventory is actually some money that's being stored there, and this money will not earn you interest, so there is some lost opportunity for not using the money stored in inventory. So somehow some companies might have some financial limitations on the total value of the inventory kept at any time. So this is another resource constrained multiple EOQ system. So in this case, either due to stocking space limitations or financial limitations, we have to, somehow modify the basic EOQ model that's being used for multiple stock keeping units in order to take such limitations into considerations. As an illustration, for instance, here we have 3 different stock keeping units. Each stock keeping unit has its own ordering cycle that optimizes its total cost. And of course, we treat the 3 items independently. But then, okay, sometimes at certain points of time, you might have a total amount kept in inventory that's really large. For instance, if you take this point of time and look at the amount of inventory there, you'll see that actually the total number of units kept in inventory is quite large. Okay, well, your warehouse may not be able to store that large quantity at that specific time. So in this case, somehow we have to modify our solutions. We have to adjust the values of the calculated optimum ordering quantities for the 3 items so that we do not exceed the storage limitation defined. Let us have an example to illustrate this idea. In this example, we have 3 items purchased in a shop. The relevant cost and demand parameters are given in the following table. So we are giving the demand information, the unit cost, the ordering cost for each item. And the cost of capital is 25%, and of course it's dollar per year. Now we have a constraint here that says the shop never has more than $30,000 invested in the inventory of these items at one time. This means what? At any given time, the total value of the stored quantities of the 3 items should not exceed that limit, $30,000. So the question here is, what would be the lot sizes that we should actually order in this shop so that this budget limit is not exceeded? In order to solve this problem, we start as usual. We start by applying the EOQ formula to calculate the optimum ordering quantity for each item independently. Let us see how this is done. Here, we calculate the EOQ values for each stock keeping unit independently. And these are the values that we have calculated. 172 for the first one, 61 for the third, 63 for the second. Now, for each individual item, the maximum inventory level that can be reached is the calculated EOQ value, as we have learned before. So at some point of time, it might happen that the maximum inventory level for all the three items, independently of course, are reached. In such case, the total amount of inventory is going to be the summation of these three values, the calculated EOQ values. Okay, but in this specific example, we have learned that the amount of money that we are allowed to store at any time should not exceed 30,000. So it's like we need to convert the maximum inventory quantity into its equivalent monetary value. And this is done by calculating the maximum inventory value, which is the EOQ value, by the cost per unit for each individual item. Then we sum up the values, as you see here. The total value is found to be $35,835, which exceeds the limit of $30,000. So in this case, I cannot actually rely on the solution that actually calculates the EOQ value for each item independently, because it might happen that at certain point of time, I can reach or exceed the limit, the financial limit defined in this problem. So in this case, we have to adjust our solutions. The adjustment is done very easily by calculating the ratio 30,000 divided by the total or the maximum monetary value of the items kept in inventory, which is calculated here. Okay. Now, when you take this ratio, you will get the number 0.8372. Now, what we are going to do is we are going to take this factor multiplied by the EOQ values calculated for each individual item, and this will give us the values given here in this slide. So for the first stock keeping unit, it's 144. For the second one, it's 52. For the third one, it's 51. After doing that, we recalculate the maximum monetary value of the items kept in inventory and double check again our numbers. Did we exceed 30,000 or not? Most likely the value is going to be less than 30,000, and in that case, well, if you have some remaining amount monetary value, then this can be distributed or assigned to any one of the three items. So this is an illustration of how to treat these kind of problems. The general procedure used for treating the resource constraint multiple EOQ models is done as follows. First, suppose that n items have unit costs of V1, V2, V up to Vn, and these unit costs can be replaced by actually unit volume or unit weight. This will give you the same kind or the same analysis. And the total budget available for item for them is C. This is the limitation that should not be exceeded. And again, this could be in terms of monetary value, or it can be the volume, or the area, or the weight. Then the budget constraint can be written as, you just simply multiply V1 times Q1 plus V2 times Q2, and etc. And then, okay, you have to check if this summation in the left-hand side is less than or equal C. And of course, as we have seen in the illustration before, the values of Q1, Q2, Q3 are originally the EOQ values for each item individually. Now, if we found out the left-hand side based on the EOQ value is less than or equal C, then this means the restriction is not exceeded by the EOQ values calculated, and therefore the EOQ values calculated are going to be the optimal values that we are going to use in our solution. But if this is not the case, just like the illustration that we had in the previous slide, then we calculate what first we have to check if the values of V1 over H1 equals V2 over H2, etc. or not. If that's the case, then we can prove that the optimal solution is, as a matter of fact, to calculate Q star as M star times EOQ for each stock keeping unit, where M is simply the ratio between the capacity or the monetary value available divided by the summation of the V times EOQ. This means what? This means actually the rule that we have applied in the illustration done in the previous slide is going to yield actually the optimal solution for this multiple resource EOQ system if the values of the ratios between the value V divided by the inventory carrying cost per unit is actually fixed for all items. This will give us the optimal solution for this specific problem. Now, this may not be the case. Now, if this is not the case, then it's good enough to use this approximation, okay, to calculate the values of the order quantities for the N items that we have in inventory. This will not give us the optimal value, okay, under that condition, but at least it will give us a good enough solution to the problem. Luckily, if we are talking about financial terms, like V is the unit value and H is the inventory carrying cost per unit, and if the inventory carrying cost per unit is calculated based on the interest rate or the cost of capital I times V, then this is going to be the case. As a matter of fact, I mean, this condition, which is defined here, okay, this condition is going to be valid, okay, in this situation. In this case, of course, we can rely on our solution and it will give us the optimal solution to the problem. Otherwise, if this is not the case, then we do not have the optimal solution. We know that for sure, but at least we have a good enough solution that is close to the optimal. And remember here, the idea of the sensitivity analysis that we have presented at the beginning of the lecture for the EOQ model can actually help us here, because the value that you calculate using the EOQ model, if you have some deviation from that value within 10%, okay, minus 20% plus, then actually your deviation from the optimal cost value is going to be minor. So when we apply this concept of insensitive EOQ model to the current situation, the multiple items resource constraint system, then we can conclude that the solution that we will get generally by using this approximation is a good enough solution and is very close to the optimal solution if it is not. The second topic that we will talk about here, which is related to managing the inventory of multiple items, is the power of two policy. The idea here of the power of two policy is very simple. We know that when we have multiple items inventory, we might have different ordering cycles for each item. So for instance, the inventory level diagram for one item could be as such, okay, with ordering cycle, for instance, of 2 weeks. We can have another item, inventory item, that looks like that, with ordering cycle of let's say 2.5 weeks, okay, or 3 weeks. We might have another item that has an ordering cycle of 5 weeks, and so on. So in this case, the ordering of these different items will be done at different points of time. And this actually sometimes will be a big hassle for any inventory manager. Why? Because he will have to take care of hundreds of items in inventory. Each one of them will have ordering time that's different from the other items, and the differences in the optimal ordering cycle can be quite large. So in this case, it's more convenient to have some common ordering cycles that can be a little bit different from one item to another, but they share common ordering points of time. This is actually exactly what the power of two policy offers here. So the idea here is, well, in the beginning, you can define specific time points of time, like the ones illustrated here in this timeline, and the length of the ordering cycle in that line is fixed, which is, we call here, the basic planning period. And this basic planning period is denoted as T sub L. This could be one shift, 1 day, 1 week, 1 month, okay? And then for each individual inventory item, we adjust its optimal ordering cycle time such that it will be 2 to the power L, okay, where L here is an integer value, times the basic ordering or basic planning period, which is T sub L. So for one item, for instance, I might choose L to be 0, and this means I will order every TL. Another item, and that's exactly the case that's presented here. So I will order every TL. Another item might have L equals 1. So in this case, I will order every 2 TL. So every 2 TLs, I will make I will place an order for that item. Another item can have L equals 3. So this means what? This means we will order every 8 periods, and so on. Okay, so this is how the power of two policy is applied. So this means what? This means for each individual item, I can have an ordering cycle that's not necessarily the optimal value for that item, but a value that's close enough to it, such that it will be expressed, or it can be expressed as 2 to the power L, where L is an integer value, times a basic time period, which is T sub L. The question is, if we apply the power of two policy, what would be the performance of this policy for the different items? And this performance actually can be measured by comparing the total cost calculated when we apply the power of two policy with the total cost when we use the optimal ordering cycle of an item. To see that, let us first have a look at the total relevant cost function, TRC, as a function of the ordering cycle T. Remember, it's basically when it was defined using the order quantity Q, it was expressed as such: AD over Q, that's for the total ordering cost per year, plus the average inventory carrying cost per year, which is HQ over 2. Now, we can actually replace Q over D, okay, by the value of T, which is the order cycle. This means we can re-express the total relevant cost function as a function of the ordering cycle T as such. So it's going to be A over T plus H dt over 2. Now, of course, similarly, we can also calculate Q star, which is the optimal economic order quantity, and equivalently the value of T star, which is the optimal ordering cycle. And of course, for the basic EOQ model, it's going to be square root 2A over DH. All right, so to simplify our calculations, we are going to set G to be DH over 2, and this means we can directly calculate T star as the square root of A over G. Now, T star again is the optimal ordering cycle of an item. Now, when we apply the power of 2 policy, we will have some deviation from that optimal value. In order to illustrate this concept, okay, if we draw the total cost function as a function of T, okay, which is the ordering cycle, it's going to have the same look as the total relevant cost function as a function of Q. It's going basically to have the same shape. Well, in this case, the optimal value, T star, is going to be at the point where the total relevant cost has its minimum value. Now, when we apply the power of 2 policy, this means for that specific item, I'm going to choose a value for L, okay, a value for L to substitute in this relationship. So I'm going to choose a value of T order cycle that's 2 to the power L times T sub L, the basic planning period. And when I do that, well, basically I'm going to obtain a value that's not necessarily exactly as T star. It's going to be either a value that's less than T star or greater than T star. This means I will have some deviation from the optimal value when I apply the power of 2 policy. Remember, again, the subject of sensitivity analysis, okay, will pop up here, because in sensitivity analysis, as we mentioned earlier, you can have values that are below or above the optimal value, and the difference or the deviation from the optimal total relevant cost is going to be minor. Same thing applies here. So when we choose a value that's less than T star or greater than T star, such that I fulfill the method of calculation for the power of 2 policy, this means I'm going to have either a value less or more than the T star value. Now, in order to see how the value that we are going to choose is different and how does that affect the total relevant cost, then generally we have to choose the value of L such that the total relevant cost is going to be bounded by 2 values. Okay, the value of the total relevant cost when L plus 1 is used, and the value of the total relevant cost when L minus 1 is used. This means we are talking about, as a matter of fact, 2 points here. So it's like we have here 2 limits. Okay, that's the limits that we will obtain at the values of L plus 1 and L minus 1. And in between, we have a value for L, okay, that is close enough to T star. Well, in order to facilitate our calculations, the lower and upper bounds can be defined using what? Using T star. So here, the total relevant cost, when you go back to the main formula that's used for calculating the total relevant cost as a function of T, okay, when we use T star, okay, as the lower limit, okay, or let us say 1 over square root 2 T star as the lower limit, and square root 2 T star as the upper limit, this means it's like we are redefining the basic period to be some value, okay, that's within some range from the T star. This is just a simplification. Instead of using or calculating the value of the total relevant cost at L plus 1 and L minus 1, well, instead of that, I use T star, okay, in my calculations. And when I do my substitutions, well, I get the two limits defined at 1 over square root 2 T star, and the other limit at square root 2 T star. So in this case, okay, the basic or the ordering cycle for that specific item is going to be 2 to the power L times TL. What we are looking for here is actually the value of L, okay, which will define the ordering cycle for that item. Now, well, using these ideas, we can do some mathematical manipulations, okay, by doing our substitutions of the T star over square root 2 and square root 2 T star, and we can do our substitutions. And when you do that, you'll find out that the total relevant cost that's calculated using the power of 2 policy for that item is going to be within some factor multiplied by the total relevant cost when the T star is used. Well, this can be a representation of how much of a deviation I will get when I apply the power of 2 policy. Well, then next, by knowing that the total relevant cost function is strictly convex, okay, which means it takes that shape basically, it's a convex function. So this means what? This means if you go backward, okay, L minus 1 or forward L plus 1, okay, you will usually expect that the cost is going to be higher than the value that's close to L when you use, of course, L in your formula. And I'm not going to go through the details of the calculations, but the point is, at the end, the calculations here are based on assuming a uniform distribution of how far you are going to be from these two upper and lower limits, etc. I'm just concerned about here the final result. The final result is, as you can see, it says, well, when you apply, as a matter of fact, the total relevant, the power of 2 policy, and you calculate the total relevant cost accordingly, you will see that on average, the deviation is going to be about 6% from the total relevant cost at the optimal value when you use T star. Okay. That's basically simple substitution in the values. And then, well, most of the items will not necessarily have that exact value, but sometimes they might have some variations. So in the textbook, what they do is they assume that the distribution of the values are going to follow a uniform distribution between these two limits, okay? And then when you do that, you will find that on the average, the deviation is very minor, which is 2% above the total relevant cost value. So that conclusion, I'm not, of course, asking you to do or to know the details of these calculations. Okay, you can have a look on more on the proof for this final result in the textbook. But the point here is I'm concerned with the final result. The final result says, well, the deviation is not that really big when you apply the power of 2 policy. On the long run, the average deviation from the optimal value that you are going to get is about 2% more than the optimal total relevant cost if you apply or if you use T star as your ordering cycle time. This final result is very important, and it goes with the same way as we illustrated earlier for the topic of the sensitivity analysis of the EOQ model. Now, let us have an example to illustrate how the power of 2 policy is applied. Suppose we have an item in which the demand is 5,000 per year. The unit price is 375 Egyptian pounds per unit. The cost of capital is 20% per year. The ordering cost per order is 300 Egyptian pounds. And we have 300 days a year. When you calculate the Q star, it's going to be 200 for this data. And T star, of course, is going to be 12 days, almost 12 days. So we are interested in, well, selecting the value of L, okay? As you notice, 12 is between 2 to the power 3 and 2 to the power 4, which are 8 and 16. And of course, here, the basic planning period is 1 day. So in this case, either you order every 8 days or every 16 days, okay? So we are interested to compare the costs associated with these two alternatives. If you are going to order every 8 days, then the total relevant cost is going to be about 16,000 Egyptian pounds. And if you decide to order based on a cycle of 16 days, the cost is going to be 15,000. So apparently, of course, our choice in this case is going to be 16 days with a cost deviation of 4.17% from the optimal order period of 12 days. So this is how we apply the power of 2 policy, and some insights about the optimality of or the deviation from the optimality for the power of 2 policy. That's it for today. Thank you for your attendance, and inshallah, we will have a tutorial on the EOQ model, inshallah, this week. Thank you and see you.